Okay, this is the lecture video for MAC1105. This is a continuation of section 5.4 where we're solving exponential equations, and this will cover examples 20 through 29 in the section 5.4 outline. Okay, so in example 20, we see two individual logs, and we're going to combine these so that we can use the procedures for a one log problem. As you recall, all through, let's see, this began with, let me take a look backwards. In numbers 13 through 25, the technique that was being emphasized was a single log, no log on the other side. And the procedure that we used is to simply rewrite this in exponential form by pushing up the base, going and grabbing the expression that was by itself to become the exponent, and that argument went over and took the place of this value that became the exponent. So that's the technique that has been used all the way up through 19. Or all the way up through 19. So now we get close to number 20, and as we got close to number 20, beginning with number 19, we saw that there were individual logs on one side, but that can still be approached the same as numbers 13 through 18 because you can combine these to create a single log, and that is the case in number 20 as well. Okay, you have two individual logs. They are joined by a plus sign. That means their arguments used to be a product. And that's how you can rewrite these two logs as a single log. So you can condense them into one log by expressing their arguments as a product. Okay, in this way, we can take the same approach that we took in numbers 13 through 19. We have a single log on one side, no log on the other side, because again, that'll be a different approach, and we'll hit that at some point in this section. Okay, so we're going to come to the point where we have a single log here, and we're going to rewrite this in exponential notation. We do that by raising the base, going to the opposite side of the equation where we go to find our exponent. And then this entire argument jumps over and takes the place of the number that became the exponent. So x plus 6 times x plus 5. That was the argument, and now it's over on the right side. We're going to expand that by FOILing. So we're going to go x times x. That'll give us x squared. We're going to go x times 5. That'll be 5x. Continue FOILing right here for this inner product. That'll give us 6x. And then 6 times 5 will give us 30. And then here we have 2. Because we have a second degree equation, we're going to need to bring everything to one side, and we'll attempt to factor. So I'm going to bring this 2 over here, and then we'll continue the problem right up here. Okay, so we've zeroed out one side, and on this side we have an x squared term. We have 5x plus 6x is 11x. And then as far as our constant, we have 28. Positive 28. Okay, then we're going to try and factor that. I'm going to use the factoring technique of guess and check, and that's because the leading coefficient is 1, so it's easy enough to guess at the times tables that are going to work to multiply and give you a 28, but add and give you 11. Okay, it's pretty common to know the multiples of 28, those being 7 and 4. 7 times 4 multiplies to give you 28, but adds to give you 11. So those are going to be the numbers that work. Doesn't matter which one you put in the first parenthesis and which one you put in the second parenthesis. They're both the same sign. Okay, when this last term is positive, these signs will be the same, and this is what they will both be. All right, so we have it all factored. Now we're going to ask ourselves, what are the solutions to this equation? In other words, what are the zeros? And because both of these factors, when we factored the problem, because both of the factors are first degree and have a leading coefficient of 1, it's very easy to tell what the zeros are, even without creating those little individual equations. Just what would make this 0? -7. What would make this 0? -4. And then we have to be careful of, when solving anything that has a log expression in the original equation, you got to be very careful that the values you're reporting for your solutions don't create a negative argument. Remember, you have to reject those values if they're not in the domain. What is in the domain? Anything that keeps the argument positive. Must keep the argument greater than 0. It cannot be equal to 0. It cannot be negative. So let's see. Do either of these values need to be rejected? If you put a -7, and you have to consider them in both of the original logs expressions that we had. If you put a -7 right here, it creates a negative. It also creates a negative here. So we have to reject this solution. Then how about the -4? If we put a -4 in there, it's okay. -4 plus 6 is a +2. So it keeps this argument positive. If we put a -4 in here, that's also okay, because -4 plus 5 does keep the argument positive. So this we're going to keep, and the -7 we're going to reject. Okay, so exact answer, -4. If you write it, correct to 4 decimal places, it would look like that. Okay, moving to number 21. In problem number 21, again, we see 2 individual logs, yet we are trying to use the technique where we rewrite the log expression as an exponential expression. And the only way you can do that is if you have a single log on one side and no log on the other side. So we work to use the properties from the previous section 5.3. And one of those properties said that if you have 2 individual logs separated by a minus sign, that means condensed as a single log, it used to be a quotient. The arguments formed a quotient. So that's how we're going to recombine these 2 individual logs, through the creation of a quotient. This first argument will be the numerator of the quotient, and the second argument after the minus sign will play the role of the denominator. This single log will still have the same base as the 2 individual logs. And now that you have single log on one side, no log on the other side, now you can rewrite it in exponential notation by simply pushing up this base, still using it as a base, but an exponential base, not the base of a log. So push that up, go over to the opposite side and grab that number, which becomes the exponent, and this entire argument jumps over and takes the place of the number that is now acting as the exponent. So x plus 16 over x minus 8. Okay, so now I'm going to finish this up here. We now have 25 on the left-hand side, and we have x plus 16 over x minus 8 on the right. Now trying to get rid of the fraction, so we can continue solving without the fraction. We're going to cross multiply. Okay, so you can just cross multiply going this one way, and that'll get rid of the fractional nature of this problem. So it'll be 25, you're cross multiplying that with the expression x minus 8, and this x plus 16 stays on the right hand side. Okay, now carrying that 25 straight through the parenthesis, distributing it to each of the terms. It'll be 25 times x and 25 times negative 8. Okay, now we have a linear equation, non-fractional, and so at that point we're just going to get all the x's on the same side and constants on the opposite side. Okay, so if we bring all the x's over here, I'm going to bring all my x's to the left. That would be, let's see, 25x minus 1x would be 24x. That would leave us with no more x's on the right. And since all the x's are on the left, then it makes sense to bring all the constants to the right. This negative 200, when it moves over here, is positive 200. Showing it with that arrow is the same thing as adding 200, adding 200. So this will be 200 plus the 16 that was already there. And then you can use your calculator to help you with the division. Let's move this over a little bit. Okay, so that'll be dividing the 24 right off of the x, likewise on the right-hand side of the equation, and that'll give us x is equal to 216 divided by 24, and that's 9. Okay, make sure that you check the number that you are plugging into each of the individual arguments to make sure it doesn't need to be rejected, that it doesn't create any kind of a negative. So if you put a 9 right in there, that certainly does not create a negative in this first argument, nor does it create a negative in the second argument. 9 minus 8 is 1. So that answer is perfect. Approximate to 4 decimal places is that. Okay, going to number 22. This time we have 3 log expressions. Again, we're attempting to use the technique where you rewrite the log in exponential notation, and you can only do that if you have a single log, no log on the other side. So any 2 logs that are connected by a plus sign, that means that these form a product on with the arguments. You're going to do a product of the arguments. However, anything that comes after a minus sign, that argument belongs in the denominator. So you will have a fraction, but first we're going to form a product in the numerator. Okay, so it's going to be log of x minus 6 times x minus 4. We formed a product out of those arguments because they were joined by a plus sign. And then this x, that expression that comes after the minus sign, means that that argument belongs in the denominator, each one of these bearing a base of 2. And so that single log still has that same base that all 3 of these individual logs had in common. On the other side, we also have a 2. Now we're going to take it out of log notation and into exponential notation. That requires you pushing up the base, going to the opposite side to grab that number or expression, which will play the role of the exponent, and then this entire fractional argument is going to jump over and take the place of this number that just became the exponent. So it'll be x minus 6 times x minus 4, and we'll FOIL that out, over x. Okay, why don't we do a couple things just to conserve space and not rewrite it again 10 times. So I'm going to say part of this verbally. 2 squared is 4. We're going to take this 4 and multiply by the x so that we get rid of the fractional nature of this problem. So 4 times x is going to give you 4x on the left, while what remains on the right side at that point, since this x will be yanked right up here and no longer be in the denominator, so that we no longer have a fraction, what remains over here is just x minus 6 times x minus 4, and we'll go ahead and we'll FOIL that out. It'll be x times x times negative 4, and for that inner product, it would be negative 6 times x. And then this last term times this last term would be negative 6 times negative 4, positive 24. Okay, so we have gotten rid of the fraction, and now we are going to solve a second degree equation. That's going to take getting all terms on one side. So take this one term that's on the left side, bring it over here to where everything else is. So we have zeroed out the left side. This is now over here, appearing as a negative 4x. That's the same thing as minus 4x minus 4x. We have an x squared term here. As far as our linear terms, in other words, our first degree terms, we have negative 4 and negative 4. That's negative 8. And then combined with a negative 6, that would be negative 14x. And then we have that positive 24. Okay, so now we're going to have to think of, I'm going to use guess and check method again rather than rewriting the middle term, just because when the leading coefficient is 1, it's easy enough to just think of the times tables combos that are going to work to multiply to get you 24, but add to get you 14, and that would be 12 and 2. Okay, 12 and 2, super common multiples or factors of, not multiples, factors of 24. Very common to use 12 and 2. And now we just have to think of, what do we do with the signs on the 12 and the 2? This means both of the signs will be the same here and here. They'll be the same, and this is what they'll actually be. Okay, and check that. Negative 2 times negative 12 is positive 24, but when you combine negative 2 and negative 12, you get a negative 14. So those are the numbers and the signs that work. As far as the solutions, or what we also call the zeros, those would be, what zeros this factor out would be 2. So it is a solution. What zeros this out would be 12. But are they actually solutions for this log equation? Any number that you claim is a solution must be in the domain. So we need to check to see whether we should reject any of these values. If this value makes any of the individual arguments negative, it is to be rejected because it's not in the domain. If it's not in the domain of one of them, it's not in this solution set. So let's see. If I was to put a 2 right here, do you see how it would be? Okay, should we reject any of the x values? Okay, checking out that very first log expression. Notice that if you take this 2 and put it right in here, it's going to be 2 minus 6. You would then have log of a negative argument. This is called the argument. It does not matter what base it is. If that argument is negative, the value that caused that negative argument needs to be rejected. No need to check it out in any of the other log expressions. It's already ruined the first one. Okay, then 12. Would the 12 need to be rejected? Again, if it fails any of the arguments, you have to reject it. Okay, so 12. If you put a 12 right in there, you're good. 12 minus 6 is positive 6. We're good. 12 minus 4, positive 8. We're good again. 12 right there would just be positive 12. So this is fine for all three of those individual logs. So 12 is fine, substituted into all three log expressions, and therefore it's good. Okay, so just a little bit of practice in the last couple of problems, learning whether or not. We in example 20, we had one where we had to reject one of our values. Sometimes turns out you got to reject both of them and say no solution. Sometimes they all work. Sometimes you just reject one. So we found out that 12 is in fact a solution. Approximate to 4 decimal places, it would look like that. Okay, moving to 23. Okay, now we come to a different sort of equation. And so I think I should correct what these instructions said, which I will on the outline. So where we were doing the single log technique, where we only had one log, it was up to 22. I'll have to change this up on the outline, but it doesn't change how we worked any of these problems. So all the way up to number 22, you were able to use the single log approach, where you rewrote it from a single log into an exponential expression. And then I believe we just got to number 23, and that has changed. So now we're going to be looking for a different way to do these, because even if you do combine these two and have a single log over here, you still have a log on both sides, which means you cannot use that technique that we just did in numbers 13 through 22, where we were able to rewrite the single log, okay? Once you get into this situation, then you're going to be taking a look at this property right here. If two logs are said to be equal, as long as they have the same bases, then you can continue the problem by working exclusively with the arguments m and n. So once you see that you have a single log on both sides, same base, you can discard the log and the base and work just with the arguments to continue solving the problem. So we're going to work to get that to happen in example 23 and for the next several problems. Okay, so let me check this out. And let me take a look at what we have all the way to, so this will be for this approach that we're going to use this for. This will be for examples 23 through, I believe, 25. Yes, because once we get past 25, then we just have a few application problems. Okay, so we're going to be using this approach where you just can't stop the problem from having a log on both sides, unlike what we did in numbers 13 through 22. Okay, so here I can combine these two. There's a plus sign in between these logs, which means they used to be a product. So on this side, it's going to be the log of x times 10, same thing as 10 times x. This is just the normal way we write the product of a number and a variable. Then over here, you also have a single log. Okay, when you have a log expression and no base is written, it is said to be a base of 10. So both of these have the same base. You have a single log on both sides, and therefore you are applying this property right here. You can work just with the arguments at that point. Okay, argument here is x plus 10, argument here is 10x. So that's all you're doing, is trying to solve that now. Try to get all the x's on one side because this is a first degree equation. And in doing so, you're going to have 10 on the left side and 9x on the right side. 10x minus 1x is 9x. And then solving for x by dividing that coefficient right off of the x. So we have 1 and 1/9, same thing as 10 over 9. And you just have to make sure that that is not something that needs to be rejected. Again, in these problems, be careful about reject any x value that violates the domain, or that is not in the domain. Okay, you're always doing that if the original problem already had the word log in it. Not that you introduced the word log, but that it began originally with log expressions in it. And we decide what to reject based on the fact that we know that a log the argument cannot be negative or zero. The argument for anything with log expressions in it must be greater than 0 based on the x value that you're plugging in. So plugging that in right here, fine. Plugging in it right here, you're not going to create a 0 or a negative, and there's nowhere to plug in anything. So that value is fine. This is the exact value, approximate to 4 decimal places, would mean get a decimal representation of 10 divided by 9 and round it to the 4th decimal place. So that would be 1.1111. Okay, then you're going to example 24. In example 24, we can combine these two logs on the left in the form of a product. So it will be this argument times this argument. There's no base on these two log expressions, therefore it's 10. Likewise for this log expression on the right, it is base 10. So when the bases are the same and you have a single log on each side, that's when you can disregard the log and the bases of 10 and just work with these arguments. So it'll be x times x plus 2 is equal to 15. Carrying this x right through and distributing it to x as well as 2, that gives us x squared plus 2x is equal to 15. Because it's second degree, we need to bring everything to one side and try to factor. So it'll be x squared plus 2x minus 15 is equal to 0. And if we continue working on that, I'm going to use guess and check again because the leading coefficient is a 1, and therefore we can just think of our times tables. What multiplies to give negative 15 but adds to give us positive 2? Easy enough to just come up with those on our own without rewriting the middle term, splitting the middle term. So breaking up the x squared, this times this is that x squared. Then two numbers that multiply to give you negative 15 but add to give you 2 would be 5 and negative 3. Positive 5 and negative 3. When you multiply those, you get negative 15. When you add them, you get 2. Okay, then what makes either of the factors 0? Well, what would make this factor 0, therefore it is a solution, is x equal to negative 5, or possibly a solution, because we do again have to worry about whether or not to reject numbers that are not in the domain. We'll look at that in a minute. Another solution, potential solution, what makes this 0 is x equal to 3, and then let's see if those work in the domain of this log equation. So negative 5, no good, because the minute you go to check negative 5, you should be able to plug it into any one of these log expressions where there's an x, and in plugging it into that very first one, you have a negative argument because the argument's x, so therefore it's the only place to plug that in, so therefore this has to be rejected. It makes the argument of this first log negative. So that gets thrown out. How about 3? If you put a 3 in there, it's fine in the first log, it is fine in the second log, and then there's nowhere to plug it in here. So this works, and the only solution is 3. Approximate to 4 decimal places, it would look like that. Okay, moving to number 25. One more of these problems where you're using the technique where you have a single log on each side, and therefore you can disregard the logs as long as their bases are the same. These do all have bases the same. Anytime you see an ln, a natural log expression, the base is said to be e. When you don't see a little base hanging off there, it's the only base it can have. You can combine the left side, the two expressions, into a single log through a product. If there's a plus sign separating them, that means these arguments used to be a product. So we're going to go x minus 4 times x plus 1, getting a single log on the left-hand side, and then over here we have natural log of x minus 8. Okay, once we have single log here, same base, you can drop the logs and just use the arguments for the remainder of the problem. So it's x minus 4 times x plus 1, and then over here it's x minus 8. Okay, so here it would be, if we FOIL to get rid of all these parentheses, it would be x squared, then 1x. Doing these inner products, right, that inner product right there, that would be another negative 4x, and then this last term times this last term would be negative 4. On the right side, we just have the x minus 8. We have a squared expression, and therefore to solve this, we're going to have to factor. We're going to try and factor first, and if that won't work, we can use quadratic formula. So we're going to bring all terms to one side. When you subtract x and you subtract x, which is what this arrow means, it would appear as a negative x on the left-hand side. And if you move the negative 8 as well, adding 8 and adding 8 to do so, you would end up with a positive 8 on the left side. So both of these terms have now moved to the left side. We'll continue the problem up here. Okay, so we had x squared. And then we have positive 1x take away 4x is negative 3x. And then another negative 1x combined with the negative 3x is negative 4x. Okay, 1 minus 4 is negative 3. Negative 3 combined with negative 1 is negative 4. And then there's a negative 4 here plus 8, which is positive 4. So after combining all like terms, we combined all these x's, we combine these constants. Now we have this left to deal with. We're going to try and factor that. And that would factor like this. X times x is that x squared. Two numbers that multiply to give you 4, but add up to give you negative 4 would be negative 2 and negative 2. 2 times 2 is 4. With the signs, and then when you add negative 2 and add negative 2, you get negative 4, or you can think of it like this. Last term positive means both these signs will be the same, and this is what they both are. Okay, so that means because we have matching factors that we can only have one potential solution, one potential 0, which is 2. However, does that belong in the domain? Let's make sure. So we come up here and we try to check it, and right away you should be seeing that this one potential solution that we did get violates this first log. When you go ln and you put the 2 in for x minus 4, right away you have a log expression, a natural log with a negative argument, and that just can't be. This argument is supposed to be always greater than 0 based on what you feel the solutions are. So this needs to be rejected. And because the one and only potential solution we got did not work, that means that there is no solution, empty set. You can answer like that, or you can answer with the circle with the line through it. Okay, so this is not applicable. There was no, doesn't apply. All right, compound interest formula. We were introduced to this in the previous section, and we talked about how this P is the original amount. It's called the principal. It stands for the original amount invested in your account, whereas this is the final amount. It's what your money builds into over the years. R, that is just rate as a decimal, must be a decimal. And we used it to do problems, like I said in the previous section. N is the number of compounding periods. Like for instance, if you're getting interest monthly, that means your money is compounding monthly. It is building upon its principal and interest on a monthly basis. If it says semi-annually, twice a year. So N is the number of times that the bank comes in and pays you interest on your principal and the interest that you've already earned. Those are known as the compounding periods, and that N value appears here as well as here, and then T is just time in years. So typically what happened in the last section is you were given P, you were given R, you were given N, and T. This time you're going to, so that you are using the skills that you have hopefully picked up in this section where you're using logs to solve the equation, you will be given this final amount or something that has to do with the final amount. Okay, so in this question it says, where A is the accumulated amount after initial investment, they're just reviewing what I just stated up here. So here's the actual parameters of the problem. Use the formula above to determine how long it will take the initial investment, so this is P, to grow to 32,800. This is the final or accumulated amount. If it earns a rate of 7.25%. For this to be considered a full decimal, in other words, for you to remove this, you must move this decimal 2 places to the left. Sometimes that decimal is all the way at the end and you move it 2 places to the left, and sometimes it's right in the middle of the numbers and you still move it. You want to get rid of this so that this number is usable in the formula. Must be moved 2 places to the left. So move it once to get around the 7, and then one more time. There's no number there, so it would just be 0.0725. That is the decimal equivalent of this rate given as a percentage. Compounded annually, that means N is equal to 1. They're only going to go in there and feed you interest into your account once per year. Annually means once a year. Round the solution to 2 decimal places. Okay, so here we go. We're going to bring this formula down here, start plugging in. Again, final amount is that 32,800, which we're going to put right in there. Principal, or the original amount, was 8,000. Then the formula goes 1 plus the rate divided by N, which is 0.0725. We just discussed that getting interest once a year, so that N value is just 1. And then we're raising it to a power of N times T. So N is 1. And let's see. Use formulas to determine how long it will take the initial to grow to if the account. Okay, so we don't know how long this money is going to sit in the account. We have all these numbers, and the only one that we don't have, you can only have one unknown if you're going to solve for it, is T. We don't know how long it's going to take $8,000 to build into $32,800. Given that the interest is being compounded annually at an interest rate of 0.0725. So this gives us a chance, being that this time our unknown is the T. Okay, the whole purpose of this section was for you to solve, or a big portion is to solve for variables that are in the exponential position. And that is not something that you've been able to handle by factoring, let's say, which has been the main thing that we've concentrated on to handle second, third, fourth degree problems. And now we move into situations where the variable is up here in the exponential position, and so logs take care of that. Okay, we're going to try and clean this up just a bit. In other words, this expression right here, you can also get rid of that, but first I'm going to clean up what's in parentheses. I'm going to do 1 plus 0.0725 and write this just as a single number. This divided by this is 0.0725, and when you add it to 1, you have 1.0725. 1 times t, t. Over here you have 32,800. Okay, before you go taking the log of both sides, because that is how you're going to handle this problem. You're going to take the log of both sides. You're going to get rid of this coefficient first. Before you take the log of both sides, and we're going to be taking a natural log here. You have to have the base and the exponent isolated. It cannot have a multiplier of 8,000. The base raised to its exponent must be isolated first. Okay, and we had a whole batch of problems like this on previous pages where this was one of the featured techniques. Okay, divide by 8,000, divide here by 8,000. That's going to give you a nice clean 1 point. Make this so big so I can take the natural log of both sides. 0.725 raised up to a power of t. And then over here you can do 32,800 divided by 8,000. Try turning it on. And you get 4.1. 32,800 divided by 8,000. Okay, so that's what we're looking at right now. Let me just refer you back to the batch of problems that illustrated the technique that I'm about to use. Okay, so that was, let's see if I can find those real quick. Okay, that was right here in numbers 8 through 12. It said, just like I commented a minute ago, that you need to isolate the exponential expression first. The base raised to the exponent has to be isolated, no multiplier. And then as far as you taking the log of both sides, you will take a common log if the base of your exponential expression is a 10. But if it's any other kind of base, you'll take the natural log. Take the natural log on both sides of the equation for bases other than 10. So that's what we're looking at. We have a base that's a 1 point something. It's a decimal, so it's not a base of 10. So we're going to use natural logs. Okay, we've already gotten to the point where we isolated the exponential expression, the base and the exponent. No multiplier out there. We divided it right into the number on the other side. Got a 4.1. So now we're going to take natural log of this side, natural log of that side. Okay. Okay, on this side, you don't have any kind of inverse property working to try and simplify this. That's when the argument matches the base. You know the base is an e. That does not match that, but we can apply the power property. You have a base, an argument, and a power, an exponent. And so you can apply the power property for logs, which says the power comes right down in front of the log and becomes an exponent. And you don't have to write that base of e. We know that it is a base of e whenever you're talking natural log. So we have ln of 1.0725 multiplied by t. And here we have ln of 4.1. So let's see, this says round the solution. It doesn't say anything about giving an exact answer, just round the solution to 2 decimal places. So if we want to have a solution here, that means we need to solve for the only variable that is in this problem, which is t. We wanted to know from the very beginning, how long does it take 8,000 to build into this final amount, 32,800. So if what we're solving for is being multiplied by ln of 1.075, then we can divide it right off of that t by dividing by ln of 1.0725. Whatever we do to one side, we have to do to the other side as well. Okay, that would cancel, leaving us with t. We're going to round to 2 decimal places, and we're going to put that in the calculator. Okay, so it's ln of 4.1. Close that up. Divided by ln of 1.0725. And close that up. And we get that it takes 20, and if we're going to round to 2 decimal places, 20.16 years for your initial investment to build to 32,800 when you're investing 8,000 at that particular rate. So 20.16 years. Okay, so working with a formula that was introduced in section 5.3, only this time not being given the information for how many years you're going to leave it in, but being asked to solve for that, which required the use of the kind of one of the techniques that we learned in this section, taking the log of both sides. Okay, coming to this same formula again. It says A, again, these all stand for the same thing, final amount, initial amount, the rate as a decimal, number of compounding periods, and T stands for years. So this time, we go to read the actual parameters of the problem, and it says use the formula above to determine how long it will take an initial investment. Okay, if this is the initial investment, that means this is P, to triple. This makes a comment about the final amount. If this is the original amount, then the final amount would have to be this times 3. Times 36,250. Because that's what it means for an amount to triple. So your final amount would be 3 times 36,250. Final amount is going to be 108,750. 108,750. Okay, so we have our A amount, we have our principal. It's earning 8% interest. That means that the rate is 0.08. Got to slide that decimal 2 places to the left, filling it in with a 0 if you don't have 2 numbers to slide across. Compounding daily. So in the course of a year, and they even make a comment right here, 365 days in a year. That is what N stands for. How many times in a year is the bank going to come in and pay you interest? That's what it means to compound. So if they're coming in on a daily basis, they're going to come into your account 365 times and compound that interest. Okay, so here we go with the work. We're going to start it right here. Just to conserve space, I'm not going to write that formula all over again. We can just look at it right here. So final amount is this tripled amount. It's 108,750. Okay, then we're going to come to the other side. The principal is 36,250. Okay, and then it goes 1 plus r divided by n, 1 plus r, which is 0.08, divided by n, which is 365, and then raised to a power of n times t. Once again, n is 365. The question is, how long will it take for this initial investment to triple? So they are inquiring about time. Time is the unknown, which is part of this exponent right here. Okay, so if you continue that problem, we're going to do exactly what we did in the last problem. We are going to get a single number here. Then you'll have a base raised to an exponent, which needs to be isolated. Therefore, we're going to strip away this 36,250 right off of that base and exponent so that we are isolating our exponential expression. So first, let's get a single number right here. We have 36,250. Do some calculator work here. So 0.08 divided by 365 is, okay, so in order to have good accuracy at the end, you're going to want to hold on to at least 5 or 6 numbers after the decimal, because they can get pretty picky about you rounding off too soon in the problem. So first, let's recognize that if this is a negative exponent, if you want to take this out of exponential notation, this is like in scientific notation. So if you want to take it out of that notation so that you don't have an exponent right here, anything that has a negative exponent just means that it's really smaller than this coefficient that you're seeing. To make this smaller, take that decimal to the left this many places. So once to get around the 2, and then 3 more times where you're going to have to supply the 0. That's just taking this out of scientific notation so you can have something to write right there on your paper without writing all of this. Okay, so it's 1 plus 0.08 divided by 365 is, slide it around there, and then 3 more times, filling in the 0. So 1, 2, 3, we slid around the 2. We just took that 4 places to the left, which is what that negative exponent means. And then you can even write a few more numbers if you want to have some good accuracy here. So 1, 9, 2. And then we are raising that up to a power of 365t. Okay, then, because it's not in scientific notation anymore, you can add this to the 1. So it'd be 1 plus 0.00029192. Oh, I put a parenthesis there. Sorry about that. You really don't even have to put it in the calculator. You can just write this like this. 36,250, and this is 1 point. Just add this on to the 1. 1, 2, 3, 2, 1, 9, 2. Okay, meanwhile, we've had the 108,750 over here the whole time, and we are trying to isolate the base and the exponent that we have on the right, because otherwise we can't take the log of both sides in order to solve for t. So we're going to strip off this multiplier. Likewise on the other side. Okay, so 108,750 divided by 36,250, and that gives us 3. 3 on the left right here. I'm going to finish the problem right up here. And then on the right-hand side, we have the 1.0002192. 1.0002192 raised up to a power of 365 t. I'm going to move this over just a bit so I can have room to show that I am taking the log of both sides. So remember, whenever you are taking a log of anything other than base 10, you're going to be taking a natural log, just like we did in the last problem. So natural log here, natural log here. Okay, so let's see. Now that I have this big arrow in the way, I'll have to move it over again. Okay, so let me just give myself some room here. So what we have here now is that we have natural log of this base raised to the exponent. Can't use the inverse property where this matches the base because they don't. So we're going to use the power property. Power property comes right down, becoming the coefficient. So now it's 365t times the ln of 1.000292. And then over here we have ln of 3, and that ln of 3 is 1.09861. Just trying to hold on to a significant number of digits so that we can get an accurate estimation of what's going on here. Okay, so then let's see. Now what we can do is we have 365 times the decimal that represents ln of 1.0002192 times t. T's wedged right in there, and we can get a single coefficient instead of one here and then a number in back of it. So let's go ahead and do that. We have ln of 1.0002192 times 365. Okay, so all of that multiplied together is 0.079999 times t, and then over here we have the 1.09861. Then we're going to divide off that coefficient. Likewise over here. And getting an approximation for t to 2 decimal places. Now we can round more severely. So 1.09861 divided by the answer that's still in the window above. Just press second, answer. Second function, answer is right next to the enter key right there. See where the minus sign is? And press enter, and you get 13 rounded to 2 decimal places, 13.73. Approximately 13.73 for this money to triple. Okay, last problem. Oh, almost last problem. We still have 29 as well. So example 28. Now we move to a compounding interest formula that doesn't have the n in it, and that's called the continuous compounding formula. We also worked with that in the previous section, section 5.3, and we continue to do so here, only we're going to be looking for time. And that's going to allow us, like we have in the last 2 examples, to use these log properties for solving equations. So it says A is the accumulated amount, in other words, the final amount, just like it means in the formula that we used in examples 26 and 27. P is still the principal or the initial amount. R is the rate as a decimal. T is time in years. And E is just a number. So the number 2.71, it's a run-on decimal. So let's start plugging in based on what they've given us. So parameters of the problem are down here. Use the formula to determine how long it will take an initial investment, that's P, right there, to increase by 65%. Okay, well, here's the original amount. We want to find out what they're talking about as far as the final amount. All they have described to us is that that final amount is going to be this increased by 65%. So here's the original amount, 15,000. Increased means added on, that it increases. And 65% doesn't mean add 0.65. It means 65% of the original amount is added on to the original amount. It increases by 65% of the original amount. So here's what you started with. Here's 65% of the original amount. So it's going to grow into this amount. 15,000 plus 0.65 times 15,000 is, okay, it's going to grow into 24,750. 24,750, and that will be our final amount. This is our starting amount. This is our final amount. And the interest rate is going to be what you see right up here, but in the form of a decimal. Sliding that decimal 2 places to the left would give you a decimal equivalent of 0.0475. Okay, now plugging into this continuous compounding formula. Look for them to be saying this whenever you're using this formula without the ends in it. Okay, so final amount, 24,750. Continue that formula and you have the principal amount on the right side of the equal sign. Principal amount was 15,000. Then it's times E raised up to a power of R times T. That rate, as I discussed, has to be a decimal, and this is the decimal equivalent of 4.75%. 0.0475 as the rate times T. That's the power on that E. So now you're solving once again for T, which is up in the exponential position, and you're going to need logs to take care of that. As commented in the last few problems, this base and exponent needs to be isolated. Therefore, this coefficient of 15,000, you're going to divide that right off of there. Likewise on the other side. Okay, so you're going to have the base and the exponent isolated. And then over here you'll have 24,750 divided by 15,000. And that would be 1.65. 24,750 divided by 15,000. That'll be 1.65. Let me give myself some room to squeeze in that log. Okay, so when trying to solve something in exponential notation like this, you'll take the log of both sides. When the base is in E, it's common log, but any other time it's natural log. Okay, so natural log here, natural log here. Now in this particular problem, you can use the inverse property. The inverse property states that if the argument is the same as the base, and the base on natural log is E, if these two match, they cancel with each other. Take the log with it, and down comes the exponent. In the previous 3 problems, we've had to swing that exponent in front of the log applying the power property. But here the inverse property worked, and so we could bring that exponent down just by virtue of the inverse property. So 0.0475t, and then this is just going to be a decimal. We're going to get that off the calculator. So ln of 1.65 and I'll just write this even though we're leaving the whole thing in the window. Just put that many decimals, then we're dividing this side by 0.0475 to isolate that t. Likewise right here, 0.0475. Okay, we actually have this to a more exact form. It's still in the window, and we'll be dividing by 0.0475. Okay, so that gives us, and again, we are rounding to 2 decimal places. So that gives us 10.54. So t on the right side of the equation still remains. Coefficient got divided off of there. This divided by this was 10.54 years. Okay. And I believe there's a number 29. There is, and this will be our last example. So we've got tons of examples in this section, which I know is going to be, pretty new for you. You don't do anywhere near as many sections of solving logarithms as you do with factoring and solving equations using techniques that are related to that. So this warranted having more examples. So in this particular problem, you're using continuous compounding formula again. Let's come down here to see what to plug in. Use the formula above to determine how long it will take. So once again, we're looking for how long it will take. We are trying to solve for t. An initial investment of 15,000. That means this is P. To increase by 60. This looks like it's the same exact problem around the solution, so we do not need this. Okay, so we've already done this one. Thought there was going to be 29 problems, so it stops at 28. Okay, that concludes the second part of section 5.4, working all the way to the application problems.